some special features uh, in the sense that it can be thought of a limiting distribution, and at the same time it can take care of the events with very low probability. So usually probabilities are controlled by a fixed number between 0 and 1, but here you will see that a number which is not lying between 0 and 1 is also controlling the probability distribution. So whatever you have seen mostly in Bernoulli, binomial, geometric, and negative binomial, everywhere p was there, and that was lying between 0 and 1, and you can easily see that, well, if the p value of p is large or close to 1, you will see some feature. If the value of p is close to 0, you will see some feature. But here p will be inherent. So identifying p may not be always possible, but you can think of a model and uh, which will have very nice feature, and it will make a connection to other distributions also at the same time. So let us talk about it. It is Poisson distribution. Okay. So first let me introduce with the PDF. After that we will show how that PDF comes as a limiting sense, uh, or maybe the distribution comes as a limiting sense, and it has a connection to other stochastic processes that we will define briefly, and we will just state the connection. We will not go for the proof. We will state in such a way that you will be able to do the necessary mathematics at this level. Okay, so Poisson distribution or Poisson random variable. Poisson, okay, let us call random variable. So a random variable x is said to follow Poisson distribution. Uh, Usually written like this, or POIS. Sorry, the focus is. Okay, so Poisson lambda. If fx is of like this, e to the power minus lambda, lambda to the power x by x factorial, 0 otherwise, and x belongs to natural number set union 0, and lambda greater than 0. Okay. This is the PDF. You can see immediately that if you suppress this quantity and if you take the sum, it is a E series, and you will get e to the power lambda, e to the, place e to the power lambda and e to the power minus lambda, they will, with product, they will give you 1. So it is a valid PDF. There is no harm. Okay. So where you can use this kind of model, this is a very, very important model where the engineering and manufacturing, all those departments or all those streams are heavily using this thing. So number of defected items in a lot. So number of defected items in a lot. Okay. Number of misprints per page. Okay. Then number of, you can say that number of bad spot or defected spot on per square meter metal sheet. So number of bad spot per square meter metal sheet. Okay, and number of, okay, you can, that is not, this number is not an small number nowadays. Okay, so let us write in this way that number of spam mails in your inbox per hour. So all this kind of thing you can model with this Poisson random variable. So can you please tell me any feature from these examples which you can extract out? I mean, heuristically, need not be mathematical. Any feature which is common for all those examples. So maybe a lot is producing 1,000 items per batch. A page maybe have how many characters? 2,000 or 3,000 characters per page. A metal sheet, 1 square meter metal sheet is a huge space to hold many defected spots. And your inbox per hour can have many spam mails. So what is the common feature that you can think of from all these examples?
Sir, all these things should be reduced.
Second, please louder.
Sir, all these things should be reduced.
All these things should be
Reduced, sir. I mean, these are all unwanted things.
okay. Yes, that is the purpose. Ultimately, practically, that is the purpose. They are not. They are not one. Even that is a number of accidents. I forgot to write. Number of accidents, maybe say per day in a road junction. Yes. So all these things are unwanted. Okay, that is true. But mathematically or statistically, what are the common features among them?
Sir, they depend on the number of items.
They depend on the number of items. Okay, that is true. So here you have the possibility of number of items. Here you have number of characters. But a metal sheet, you cannot say that how many are there. So maybe this is a metal sheet, or maybe this is just, you can think as a paper, but there might be bad spot where if I touch my pen, it may bloat. So they are the bad spots. Then in your inbox, how many spam mails are coming? Well, there is a counting and number of accidents. So any common feature. As we control this thing, or one is told that it is almost all examples are unwanted, or even they are the events of unwanted situations. So just let me tell you that number of possible occurrence could be very high. So number of possible occurrence could be very high, but probability of occurrence is very low. Is it okay? Check.
Yes, sir.
Yeah.
So from these examples, how can I convert this statement?
Well,
Because
this is, yeah, it is not confirmation of the statement. It is how we can go to model this situation. We need a mathematical structure which will resemble with it, and we are proposing that we will go by a mathematical structure which will allow that in a lot, maybe 1,000 items are there, all of them can be defected, but the way we do the manufacturing, the number of defected items are less. Then the number of misprint per page, so as many characters are there, there could be a misprint. But the way we write, we try to minimize the typos. Is it okay?
yes, sir.
So that is our motivation, that how we are going to model this situation. Okay, so now you can see, before we go further, let us talk a little bit about this Poisson random variable. First, let us talk about through its moments such that we can make use of it. So, expectation of x, it is very easy. Your straightforward formula will tell you that it is x into e to the power minus lambda, lambda to the power x by x factorial. X is running from 0 to infinity. Just do this sum. One term you take out and do the sum, you will get lambda. Okay, and it is an interesting feature that expectation of x equals to variance of x equals to expectation of x minus lambda whole cube, all are lambda. So this is your homework, and this is unique for Poisson distribution. All will be lambda.
So
These
what
three.
specific terms are we give to lambda? Is there
Say
any
again?
specific? So is there any specific?
Lambda should be positive. I am coming to the more detailed significance of lambda.
Okay.
Lambda, for any positive lambda, all this thing will hold. Mathematically, all are correct. Statistically, what does it mean? We will come soon. Is it okay?
Yes, sir.
Okay. Now let us calculate the moment generating function, because that we will use.
Sir,
MG,
if this is PDF, then shouldn't we use a DX here?
so okay, so I mean PDF or PMF, you write PMF. Okay, it is discrete PDF. I have told in one class that it doesn't matter in whether I write it PDF or PMF. For your course, you may distinguish it PDF or PMF, but in higher studies, it doesn't matter. So it is denoted that the support of the random variable is this. So dx here is 1, and integration is replaced by summation. Okay. So in general, the term PDF is correct. Let me tell you, in general, the term PDF is correct. But I am sorry to also say that in many of your interviews within IIT or maybe out of IIT, if you say it is PDF, the examiner will be angry. Why are you saying PDF? Why not PMF? But correctly speaking, PDF is the right term. PMF is also right for discrete valued random variable, but if you say it is PDF, discrete PDF, there is no harm. You need to understand from the context. So MGF of X, so that is MXT is expectation of e to the power tx. Okay, so now this quantity you can write sum over x running from 0 to infinity e to the power tx, then the PDF e to the power minus lambda, lambda to the power x divided by x factorial. Okay, so e to the power minus lambda has no x involved, rest of the term has x involved. So this quantity is e to the power minus lambda, take out sum over x running from 0 to infinity e to the power, what should I write, e to the lambda to the power x and e to the power tx. So lambda into e to the power t whole to the power x divided by x factorial. Is it okay? So e to the power minus lambda into e to the power lambda e to the power t. So e to the power t minus 1 into lambda. Check whether it is okay or not. When x follows Poisson lambda. This is the moment generating function. So that means if you differentiate it with k times and put t equals to 0, you will get the kth order raw moment. Okay. Not only that, as I have told that PDF or PMF and CDF and moment generating function uniquely identifies a distribution of a random variable. So now let us move for its other interpretation. We will come back to it. As we have told here that number of possible occurrence could be very large, but the probability of occurrence is very low. Okay. So now let us try to see the model from binomial that we know. So let y follows binomial in, let us call Pn, such that you can say in this way. Then what will be the moment generating function of y? Again, go by the definition, y running from 0 to n e to the power t y, n choose y, Pn to the power y, 1 minus Pn to the power n minus y. Is it okay? Moment generating function of binomial distribution. Then you can see that here is p to the power y, here is e to the power t whole to the power y. So you can club together these two terms. So as a consequence, you can write p into e to the power t plus 1 minus Pn whole to the power n. Check. Is it correct or not? Now, as we were assuming or we were trying to model, So let n goes to infinity, what we are demanding, Pn goes to 0 such that n into Pn going to lambda. Now you can see the interpretation, the mean, a positive quantity. Is it okay? I am assuming n goes to infinity, Pn goes to 0, which is trying to model the situation such that n into Pn is going to a fixed constant, which is a positive number. N is a positive number, Pn is also a non-negative number. So n into Pn, let us take it to a fixed number, which is positive. Now, if you have this situation, what can you get from here? So this is what it is called. So MYT. So limit n, now I am looking for this limit n goes to infinity, MYT. Okay. So limit n goes to infinity, Pn e to the power t plus 1 minus Pn whole to the power n. This is what we are looking for. Now, from this relation, let us just plug in that Pn is lambda upon n e to the power t plus 1 minus lambda upon n whole to the power n, limit n goes to infinity. And from here, what you can write is this 1 plus lambda by n e to the power t minus 1 whole to the power n, limit n goes to infinity. Now, can you tell me what will be this limit?
Lambda times
So e to the power lambda times e to the power t minus 1.
So limit n goes to infinity, 1 plus a by n whole to the power n is e to the power a. Okay. So it will be e to the power lambda times e to the power t minus 1. Now you see what you have got. This is the moment generating function of Poisson distribution, and this is the limiting moment generating function of binomial distribution under this assumption. So this is same as mxt, and I have told that moment generating function uniquely identifies the distribution. So MGF identifies the distribution. That means if you have a limiting situation where number of possible occurrences is very large, but the probability of occurrence is very low, such that the product n into Pn, that is a fixed number, then you can model the situation with Poisson random variable instead of a binomial random. If you go by binomial, you will get the same result, but Poisson also can be a representative. You need not go for calculating n, because n most of the time you will not know how many. So number of accidents, how many accidents can be possible, that number you don't know. In a page or metal sheet, how many defects are possible, that number you don't know. But as a overall, you can have a, on an average per square meter, how many defected items are there, or defected spots are there, that you can very much easily identify. So here, this is the mathematical statement, or the thing that we are using here. let xn be a sequence of random variable with corresponding mgf as mxnt such that limit of mxnt equals to myt for some random variable y, then the limiting CDF of fxnt is same as fxna is same of fya for all such a where fya is continuous. So this is the mathematical statement what we have just used to conclude that the limiting distribution of binomial when n goes to infinity, p goes to 0, m into n goes to lambda, then it follows Poisson distribution. So that comes through many ways you can do the proof. The way we have done the proof is a consequence of finally this theorem that the moment generating function converges, so the CDF will converge and as well as the distribution will converge. Then we say xn converges in distribution to y. The proof is not needed for your course, but you can use it. Many books has proved in this way that they write down the binomial PDF or sorry PMF, then from there they use the same limit and they come up with the Poisson PMF. So that proofs are available in many books, so I have not done that. I have shown you an alternative proof which is also pretty easy. So from here we can conclude that in the limiting sense binomial distribution will follow Poisson. So also let us try to see the diagram.
Excuse me, sir.
Yeah, bolo.
Sir, how did you call this MXT? The final one. Did you arbitrarily choose that as MXT or?
No, this MXT is in this note. The MXT is this.
Okay.
Okay, so well, I will talk about all these things. Geometric. These codes you can play with. I have shared everything. Okay, so here Poisson lambda, I have generated 10,000 sample from Poisson lambda 2.3 and I have just plotted it. This is how the Poisson with 2.3 you will see, and then you can see that the mean part is also very close to the 2.3. Here as a Poisson as a limit of binomial. Okay, so I have chosen binomial parameter m as 100 and p probability as 0.023 and 10,000 samples are drawn. Then the Poisson lambda that you have just seen, this curve, that Poisson lambda distribution is this and binomial MP is this. So now you can see that if I remove the leveling, that this is Poisson, this is binomial, you will have no scope to distinguish that which one is Poisson, which one is binomial. Do you agree with me? If I just remove from here this Poisson and from here this binomial, can you tell me which one is binomial, which one is Poisson?
No, sir.
Yeah, so that is the point what I want to make, that as n goes to infinity or the number of possible cases in binomial goes to infinity, probability goes to very close to 0, then it is eventually the Poisson distribution. So that is what we wanted to do, and we have just done it. Now we related to this thing, we have to introduce few more terms. Let us do that. That is called Poisson process. So remember here we have talked about Poisson random variable or distribution. Okay. For large n, any other comments? Yeah, you can tell me. I am not able to follow everything from chat.
Like, is it possible that n into p of n like does not converge for large n?
Yes, that is also possible. But in that case, this Poinsot-District convergence will not hold. Yes, if your n into Pn is not converging to lambda, then this convergence will not hold. Yeah, that is possible. That is possible. Okay, so here we have talked about Poinsot random variable and its distribution in general. Okay, now we are going to introduce another notion which is called points of process. Okay, so points of process, before introducing points of process, let me just talk about what is stochastic process and as a special case, points of process. So a process or a stochastic process is a collection of random variables. So first of all, a process or a stochastic process is a collection of random variables over a index set. Okay, over an index set of maybe time or space or maybe both. Okay, so for example, in this way you can say that xt, they all are random variable where t belongs to some set t. So you can say that uh, daily temperature or daily rainfall. So for each day there is a random variable and you have the realized value of it. Okay, you can go more granular level, daily temperature across India. So for each state capital you are having one observation. So space is also varying, time is also varying. So you will have a vector valued random variable. So in that way, but you need to have a variation over, here you are having a variation over time only. If you incorporate space, then also space is allowed. At this time point, the temperature from Calcutta to Ahmedabad, each of the major city with 10-kilometer distance, you are calculating the temperature. That is also a stochastic process. Okay. Now, we are especially interested for another process, which is a stochastic process, is known as the counting process. We are dealing with discrete valued, so we are interested for counting process. Okay, so a collection of random variable or stochastic process of random variables nt, we write in this way, where t greater than equals to 0, which represents the total number of events up to time t or up to including time t. So represents the total number of events up to, including time t is called a counting process. Which satisfies the following properties. One, that nt that also greater than equals to 0. So up to time t, there may be no event, there may be some event. We have that count, and nt is typically belongs to n union 0. Second thing, that if s is less than t, that implies ns is less than equals to nt. So that means within the interval s to t, there may not be any event. Okay. So third property, s, if s is less than t, then nt minus ns stands for the number of events in S open T closed. Remember this thing, this is very crucial. S open T closed, lower bound open, upper bound closed. So as you define CDF, upper half closed, so it is also something like that, S open T closed. So if we have a process like this, then we call it a counting process. So can you please give me some examples quickly? It is non-negative integers. It is a non-decreasing function over time, and the event occurs in an interval S open T closed, can be obtained by nt minus ns. That's it.
The distribution of rainfall over a month at a particular place.
How do you count rainfall?
So I mean in terms of the this much millimeters or how much it rained.
Look, rainfall is also, in most of the cases it comes with fraction, right? Not always integer.
Yes, sir. Yeah.
Sir, we can do like population of a city till today.
Population of the city may increase, may decrease.
The number of Olympic medals after the TS day.
Say again, please.
The number of Olympic medals won by a country after
Yes,
the
number
TS
of Olympic medals won by till date. Yes, that is a non-decreasing thing.
Sir, the number of
yes, go ahead.
sir, the number of car manufacturing in a company.
A number of car manufactured in a company per day, if you take the count, it is a non-decreasing. The way you have told that the number of population, there are two things. If you just consider that, I mean, number of birth. So if you say that at time 0 there are this many people, then number of births plus newcomers, if you consider that process, it will be a counting process. Or another process which is number of death and the people leaving the city, that is another process. So there are two processes. One is a birth process, another is a death process, and then the population is a combination of these two processes. Birth and that is known as the birth and death process. That is one interesting process for I mean, a stochastic process as well as queuing theory. So that is not an example of directly counting process, but separate. If you split it into two parts, the number of newborn plus the number of newcomers, that will give you a counting process. Number of deaths plus number of people who are leaving the city, this is also a counting process. Combiningly, that is a birth and death process, that is not a counting process, because this non-decreasing thing will not hold. So again, you can also go by any of these examples. You can slightly modify, and you can take into account that the number of defected items, lot 1, lot 2, lot 3, in this way if you go, or a number of defected item produced over time, so that number will be non-decreasing. Again, a number of misprint per page, so if you go index set as page number, then also it is non-decreasing. Number of bad spot per square meter, so 1 square meter gone, another square meter has come, so that is gone. So if you have a strip of seats, then you can also count like that. Number of spam mail over your mailbox, so start from 0th hour, keep on counting. It is a perfect example of counting process. So number of accident per, so yeah, instead of per day, number of accident cumulatively, so start from January 1, and over the year if you keep on counting, then also it is a counting process. So is it okay? Any ambiguity?
No, sir. Sir, I have a doubt, sir. In the previous thing, sir, you have said that MGF uniquely identifies a distribution.
Yes.
So,
yes.
but you have shown an example like in the limiting case, the binomial distribution and the Poisson distribution are not distinguishable. So, how can we say that MGF uniquely distributes?
Okay. So what do I mean by a distribution is that the probability assigned to these numbers, what I call binomial or Poisson, it doesn't matter. You have seen this thing, right? The probability distribution over these numbers, that is the distribution, that is probability distribution. Whether I label it as a binomial distribution or whether I label it as a Poisson distribution, it doesn't matter. The probability x equals to x assigned to it, or PDF assigned to it, or CDF assigned to it, they will be the same. Is it okay?
Okay, sir. Yes, sir.
Naming is no longer important when we are, so Poisson process we have. Okay, now so we have introduced stochastic process and a special case as a counting process. Now another special case of counting process we will call a Poisson process. So let us define that thing. Poisson process, so there are different ways also to define it, but whatever way we are defining it, it is also correct and less cumbersome. So a counting process, as we have defined, is said to be a Poisson process with, remember this thing, rate lambda, okay, and lambda is positive. With rate lambda, if first, as it is a counting process, I am writing n0 is 0. At time 0, there is no count. The process has independent increment. I will explain it. Independent increment third property is this: the number of events occurring in an interval. So the number of events occurring in an interval like this, already we have defined that we will make S open, say S plus T closed, okay, follows Poisson distribution with parameter the length of the interval T into lambda. Remember, rate lambda, parameter, length of the interval into lambda. So this is length of the interval multiplied with lambda. Okay, so that means probability n t plus s minus ns within this interval, how many event has occurred. If that is k, that number is e to the power minus lambda t into lambda t whole to the power k by k factorial, where lambda greater than 0, k belongs to natural number union 0 and 0 otherwise, where typically t and s both are positive. That's it. So now tell me where you have ambiguity. I will explain what does it mean by the independent increment. We
Sir,
have
does that
bolo.
number of events formula yields a real any integer number, like number of events cannot be decimal?
And events are those things what you are able to count here.
Yes, sir. But in the formula, if we put like t and all, so it may not be a integer. Like
Which one?
then, like you have given
I
the
have,
formula, right? P and t. Okay. Yeah. Yes. I got it. Sir, I got it.
what?
The probability. Got it, sir.
Okay, so now let me explain the independent increment. So
Sir?
it means, say for example, you have time 0 here, time t1 here, t2 here, maybe say t3 here, t4 here. So t1 open, t2 close, t3 open, t4 close. Okay, so this set and this set, there is no intersection part. So if I say that the number of events occurring within this interval t1 to t2 and the number of events occurring in the interval t3 to t4, if I denote by this one as x1 and it is by x2, then x1 is following Poisson lambda t2 minus t1, x2 is following Poisson lambda t4 minus t3, and they are independent. Okay, so please check whether you have any doubt. Even not only that, according to our definition, here if we go, then this will be t2 open, t3 closed, for this region, if I say x3 is the random variable, x3 will follow Poisson lambda T3 minus T2, and this will be independent to this one also, this one also. Is it okay? What does it mean by independent increment? If you have disjoint interval, then the behavior of the random variable is independent. Is it okay?
Sir, can you please define lambda in simple terms?
Lambda is a positive number here. Any positive number will help. And the physical interpretation of lambda we got from here, that as n goes to infinity, Pn goes to 0, n into Pn is going to lambda, some non-zero number. And for the definition of this Poisson process, any positive lambda will be helpful.
Sir, length of the interval is lambda t.
Yes, see how much length of the interval into lambda. So parameter of this Poisson distribution is lambda t. Poisson distribution with parameter lambda t. When we say Poisson process with rate lambda, then the number of events occurring in a particular interval with length t, how much is the length of this interval? T, right?
Yes.
It will follow Poisson distribution with parameter lambda t. Already we have defined what is the PDF or PMF of Poisson distribution, right?
Yes, sir. Okay.
So from there you can get it.
Sir,
Yes, Bolo.
is there any upper bound of lambda that we define?
No, there is no upper bound of
Okay, sir.
lambda positive. Okay, when you will see CRT, then you will see the behavior. If lambda goes to infinity, then what is the behavior of Poisson? You will be able to see from there when we will study CRT. But anyway, so at this moment, what will be, just quickly tell me, if I say, write this thing, so expectation of NT and variance of NT. Quickly tell me these two numbers.
Lambda t.
Expectation of NT, lambda t, variance of NT,
Lambda t.
lambda t. Yeah. So for solving problem in your course, I think this much idea will be good enough. At 0, 0, independent increment, and for a interval of given length t and rate lambda, it will follow Poisson distribution with parameter lambda into t. To solve problem, this much idea will be good enough for you. In further,
Sir,
yes, please. Bolo, bolo.
Sir, the expectation and variance, if they're equal, sir, does it lead to any kind of statistical importance or physical anything?
Not much, but if mean and variances are same, and also if you check the third order central moment, then you can conclude that it is a Poisson distribution. Otherwise, for regression type of situation, there are some cases that the error is increasing as x is increasing. So as mean is increasing, then the variance is also increasing. Then those kind of situations, you can you need to remodel or reparameterize the model. Then only the usual regression you will be able to do. So those kind of rectification can be done if you can identify. Usually the error variance is assumed to be fixed when you do regression, but there are already practical situations the variance increases. Then variance increases as the regressor variable increases. So if your height is increasing, your weight is also increasing. That is also correct, but your fluctuation of the weight is also increasing with the height. Then the remodeling of rewriting of the model is needed. Is straightforward. If you go to fit the model, it will be error. So this kind of thing you have to be careful. That much I can say. And before, so what will be the probability that nt equals to 0? For any given length of interval t, there is no event. What will be that probability? That means k equals to 0. Nt minus ns
e to the
equals
minus
to
lambda t.
e to the power minus lambda t. Okay, remember this thing, we will come back to this thing tomorrow. Okay. Any other query before we leave? It has a connection with exponential distribution that we will be able to show. And many other connections are also there, but at least something we will be able to show. For your course and problem solving purpose, this much knowledge is good enough. In many other books, they have other set of assumptions from here, and they solve a stochastic differential equation, and then they come up with this. I am not going for that one, that is not needed, but this much is good enough for your understanding as well as the problem solving and model building. Any query before we leave? Okay, then thank you. See you tomorrow early morning. We will start the modeling with continuous valued random variable tomorrow.
Sir,
And back and forth we will see the connection with discrete. Yes, please say.
sir, in the counting process, can the set capital T be an uncountable set?
Capital T, yeah, this one can be real number. Yes, of course it can be uncountable.
Okay, sir, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you. কি হলো